All right. So yeah. Welcome to today's DeCal. Um, Happy to see many familiar faces. I guess I don't know. Am I happy to see that? Not quite. Okay. So James has put the attendance form in the chat. So if you just joined in, please fill it in. And we're gonna start. First, look at this beautiful picture that I processed from like I don't know 2 weeks ago. Yeah, and that red nebula up there, that's called California Nebula. Um, yeah. All right. So some announcement. Final projects. So we sent out we sent out a quiz last week. And then thank you for everyone for completing it. And the groups will be assigned by this Wednesday. So we're still trying to figure out some of the groupings. So and also as we said before, there were individual project or group project, and if you change your mind or whatever, please let us know like as soon as possible. So like that quiz that you filled in, it's not binding, right? So like if you really want to work alone or if you change your mind that you want to work with someone, just shoot us an email, and then we'll change it accordingly. Yeah, but you cannot change it after like we like in the middle of the project, which is like not quite respectful for like other people, right? And then there's gonna be a project proposal due. The proposal is basically it's like a written document that tells us that you need to tell us what you want to do, right? Like so as in like so we can check if it's feasible, if it's like within a scope of your capability. Like say if you want to like simulate the entire universe, I mean like that's probably not going to be the case. We're going to stop you from doing that. But if you just want to simulate some like solar system, that's fine. So just for us to check in with you. Okay. And then that's going to be written in LaTeX, which we will cover I think next in next lecture, right, James?
No, it'll be on Monday.
Or whatever. Yeah. So you don't have to start right now, but definitely start. So yeah, you don't have to start like writing this proposal right now. So don't worry about that. Um, but I guess if it's on Monday, whatever. Yeah, and then it's the attendance form. If anyone's watching this remotely, I don't know, fill it in, please. Right. So we're gonna start. Again, some recap. So we have two questions as usual. First one is what's the difference between this import scipy.integrate as integrate statement and from scipy.integrate import blah 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 blah, right? So what's the difference between these two? And also the second problem is really an open-ended question. So what do you do when you are stuck with debugging like or like having problems with coding, right? So we're gonna put you guys in the breakout room. And yeah. Breakout room. How many people do we have today? We have 10 people, so let's put like maybe 3 breakout rooms, I guess. No. Okay, what do we have? Don't go, Isla. Don't go, Roth. um.
Sorry, I forgot to turn it back on.
So scipy.integrate is in itself already like a function-ish thing. But anyway, but you're right. I guess like you're right. Let's not complicate the thing. You're right. So it's really like importing the package, which is like scipy.integrate, and then versus like from scipy.integrate import import like some other functions within it. So like this from thing is really from something import something is really importing some specific package. Sorry, import some specific functions. Yeah. Good. What about the second problem? The second question. Anyone, please. This is the fun question. Come on. No one, really? Sad. People don't like me. Well, because I don't want to answer this part, this one. I want to see what people
I
think.
mean, you just look it up.
Yeah, yeah. Literally, you Google. Like Google is your best friend. Stack Exchange is your best friend. Like those, like you use those to like debug your code. Or put a rubber duck next to you and talk to the rubber duck like through your code. Really, yeah. So like use Google. Like 99% of the time, like your problem has been solved by someone else. So use Google. Like just literally like search for like whatever the problem that you have, and then you get an answer. Okay. Right. So let's start like what's some new material then. So we talked about this SciPy thing on this SciPy package before, and there are also like some other packages as well. And then we're going to be introducing this thing specifically for astronomy. So there's this library for astronomers called AstroPy, and people in research do use this every day. Also depends on, but of course this depends on like what kind of research you do. Um, but personally, I've been actively using this package, this library, pretty much every day if I do research, or even when I'm doing homework. And this is a library specifically designed to make astronomy research easier. It has a lot of astronomy specific stuff, but it also can do like other general stuff as well. There are lots of packages within. So you can do like this import astropy blah 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 something something something, or from astropy blah 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 import something something something, just like the scipy integrate before. And so normally it comes with Anaconda that we installed in the very first lecture, but you may have to install it by running on this pip install astropy statement in your terminal. So if like say for example, if when you're doing homework, like you put like this import astropy something something, if it doesn't work, if it gives an error, you're most likely going to be like running this pip install astropy. But normally you shouldn't have to. So there are a lot of things you can do. And then the easiest thing you can do is units. So I don't know if any of you is in Astro 7A or Astro 7B. But in astronomy, literally lower division astronomy is unit conversion. um, you do a lot of unit conversions over there, and so like sometimes you do it by hand, but sometimes like I don't like doing unit conversion by hand because unit doesn't make sense to me. Some people go seek for help on Wolfram Alpha, which is good but not ideal in my opinion, because who cares about Wolfram Alpha? um so but yeah, so you have this astropy thing. So the statement for this is import astropy the units as u. This u is sort of like a convention. You just use that. Um, and then so you can, so basically what this does is that you can assign units to the variables, and then astropy will just keep track of them, right? So for example, like we have this. So I say the length of my table is like 1 meter, right? Without like units, you may just type one. But like if I measure some other things in centimeters, um, if like say like the width is like 50 centimeters, then if you don't put unit, or if you don't track out the units, like if you add them together, it's gonna be like 51, right? And doesn't make any sense. But so that's why you need to sort of assign units in some ways. This is not the only way to assign units, but this is the way that I use, right? Say length one is like one multiplied by this u dot meters, right? So you're with this multiplication operation, um, you assign the units to your variable as like meters, right? And then I can define some other length, and then length two equals like 2 centimeters, say for example. And then if you add them together, right, it's total L, large L. Then we'll get like 1.02 meters, right? So you wouldn't get like, if you don't assign unit, the thing, if you add them up, it's going to be 3, right? Which is not what we want. There are lots of other units that you can do. Um, um, so like Earth matters radius, you don't have to type like whatever that like 6,000 kilometers or something. like every single time, right? You can just assign like Earth radius, u dot Earth rad, or like u dot Earth mass, or like this a unit that we use in astronomy called parsecs, which is about like 3.1 light years. Um, we like you can just assign those. We'll give you some examples later. You can do it with like really weird unit conversions as well, like light year, like light years per year, like in terms of velocity, parsec per second or whatever. Um, so we'll show you this. So you can look up like what units astropy.units has like in the documentation. So which is on the side over here, right? So look it up. Like we're not gonna tell you like every single time, like use this, use that, right? Like look it up. If you really cannot solve it, then you need to ask someone, right? Normally you don't ask someone, like you code alone. Yeah. Um, so, and also you can also assign units to like the entire numpy array instead of a single variable, or like a single float. So what you do is literally multiply this u dot some units to the entire array, like we did before for the array multiplication or whatever, right? Constant times an array. This is exactly the same thing. And also you can simply extract magnitudes by doing array.value. So what this is going to give you is just 1, 2, 3, right? So that's the value, or like the magnitude of your quantity without a unit. So you retrieve the array itself. And then you can also do unit conversion by doing this array.to, and then within the parentheses, you put the units you want to convert to, right? The new units. We're gonna show an example again. So you can convert from Earth radius to parsec to light years to astronomical units or whatever, right? So those are something you can do. Yeah. Any questions so far? I'm going pretty fast, but okay, good. So let's keep going. So apart from units, you can also literally like just have the value of the fundamental constants with AstroPy as well, right? So and the way you do this is like import AstroPy.constants as con, right? Or like but like this is really what I use, because sometimes people maybe just use c directly, but c is also the speed of light, so that's why um I don't like using c directly if I want to use speed of light, right? So that's why I use this con thing. Like say for example, right? So gravity is the most important force in astronomy. Not quite, but yeah, good enough. So and then the force for gravity is gmm over r squared, right? And then we know.
Elon, are you trying to share a Jupyter notebook?
No.
Are you
Yeah, later.
all right, but like, are you typing something?
I'm not.
Oh, okay, you're not, because I thought you were. Sorry for interrupting. I thought you were typing.
No. Right. So like say gravity, right? Like gmm over r squared. So and then when you do some calculation, every time you have to write like 6.67 times 10 to 11, and then you don't know whatever the units are, right? I mean the units are crazy for the fundamental constants, or like the Boltzmann constant that you will learn later in like maybe Astro 7b, right? But then like those units are crazy, and also like the magnitude itself is like crazy enough already, right? So how do we like get an exact value or like get a shortcut on these? The way to do that is with astropy constants, right? So what it does is that like you can assign, say, over here the g equals con dot g, right? Like it literally just gives you the value of gravitational constant with units. So this astropy constant gives like it outputs the units of the constants directly. So you can work with working combination of like work with a combination of like astropy constants and also astropy units. Like c, so here there's also like c, which is would stand for the speed of light, right? C equals con dot c. And also sigma, this is the Stefan Boltzmann constant, another fundamental constant in astronomy, very important, which you will learn probably like later. This is not so important at this point. And then the way these constants are sort of labeled are also in the documentation, and you can also check the documentation of Astropath constant in this link, and then it'll just show you what the what labels are assigned to each constant, and you can just use them directly, and what is included. If like normally all the constants you use will be included, but if it doesn't, you really have to like type it your own, and then assign the units to those, and then work with those numbers. So yeah. Any questions? Good. Let's keep going then. Also, what Astropad does, this is very specific. So what I talked before is like you can use it for any like this Astropad constant, Astropad units. Those work for like anything in general, like in physics, I guess. But this is really astronomy specific, which is coordinate transformation, right? So what coordinate transformation does is like, so astronomers measure the positions of stars from the ancient times. And we want to know where they are in the sky. We want to know where they are in the actual 3D space as well. That's why we have all of this different coordinate system depending on what you study. Depending on what you study, some certain coordinate systems will be preferred over the other ones. So the way to implement to sort of like start this entire process is by importing the SkyCoord package using this from Astropad coordinates, import SkyCoords. And SkyCoord is sort of like, it's like a class. Which I will show you. You can assign the positions of like some objects in a certain coordinate system, right? So the two common ones that you will be using is ICRS, which is also RA and DEC, which stand for right ascension and declination. It's like the latitude and longitude on our Earth, right? So right ascension is the longitude equivalent. So it goes azimuthally like this, but but each line is vertical, and on declination is the latitude equivalent on our Earth, and so it goes like on the polar direction, right? So and then each line goes like I guess parallel to the line of equator, I guess. So really right ascension and declination is just a projection of the latitude and longitude into the sky onto the celestial sphere. I don't know if there's a better way to I don't know if there's a better way to visualize this, but like really just think about this coordinate system as like the position of stars in the sky as we see it, and then we project the line of longitude and latitude into a sphere of some radius, and then you will be able to see those. So those are for observers. For observers, we use like RA and DEC every day, like to specify where the target is in the sky. And then the other one is called galactic coordinates, which is also called the LB coordinate system. So the way this is defined is so L stands for longitude, B stands for latitude. So if you face to the galactic center, that's longitude 0, right? And then galactic plane is at latitude 0, which is like equator equivalent, and then longitude goes azimuthally, latitude goes like in the polar direction, right? I know this is confusing, which is why there's an illustration here, but it might be even more confusing than what I just said. Any questions? I know this is sort of like important. I know they don't teach this to you like in like actual astronomy courses. So but in some way it's important to know. right? If no one says anything, I'll just assume you guys understood this. It's fine, just like ask us questions or whatever. Okay. Feel free to stop. Myself, yeah, because I've been working with this for like quite a long time already. Right. So, but say for example, right? So if I give you a set of like RA and DEC coordinates, but I want to convert that into the galactic coordinates, right? I mean, I can do that. It's just like I convert something from a Cartesian coordinate to like a polar coordinate, right? I mean, I can do coordinate conversion in like in like in math. This is the same thing, just another different coordinate system, right? How would I do that? Apparently matrix transformations, right? But I don't want to write a matrix. I don't want to write the matrices. I wrote it once and it was terrible. So the way is to go to SkyCoord. So with I can assign like RN deck and also distance, right? So I have ICRS equals SkyCoord and the RA deck distance over here, right? So RA, so this is what we observe from the ground, right? Distance, you have to include units in all three, in all three, sorry, you have to include in all three arguments over here. Otherwise, it doesn't recognize. Like units are important, right? Like this is like almost your high school physics teacher told you like in the very first day of class. The units are important. So that's why you have to include the units in every single one of them, right? And then you can call each component of like this set of coordinate by doing this dot .ra dot dect dot distance, right? So this SkyCoord really gives you, it's like a SkyCoord object, which includes like the coordinates of some different stars, I guess, maybe, right? And then you can do coordinate transformation using this ICRS. So you don't have to, this ICRS is really just a variable name. It's just the name of the variable that I assigned to the SkyCoord object. You don't have to use that. You can use some other stuff. But you can do, but what's important is in the dot transformation too on galactic, and then it'll just like transform the coordinates for you. And then if you like call this gal variable, then you will see then the coordinate has been transformed from ICRS to galactic. And then there are also other coordinate systems you can use, like heliocentric, galactocentric. Depending on what kind of thing you're going to do, you're going to be using different coordinate systems. And then all those transformations are done in a similar way. You just have to change whatever the name is over here. And then so the documentations of SkyCoord coordinates and also astropedal coordinates and SkyCoord are in these links. So if you have questions, you can ask us or like go to the link where you're coding to see what's actually going on over there. Any questions? This is confusing. Like the first time I saw this was a disaster. Good. Okay, good. Right. Also, tables. So James is gonna cover this again sometimes, but using a different package. But like I hate pandas, so that's why I use dot tables. I feel like I'm putting a lot of personal opinions here, but whatever. So the way you do tables, say because normally data comes in tables, right? Like you have a huge table of data, like with the coordinates. Say for example, like with the coordinates or like the luminosity of the stars, like the brightness of the stars, right? Like I wanna work with those, like but in Python, but I first need to import a table. The way I do that is I first like import this package from astropedal table, import table, or not package, like function, whatever. And then so I can do like data equals table.read, and then it'll be like whatever inside that read is going to be like this should be a string, sorry. Yeah, sorry, this should be a string. Is the path to your file or like the name of the file. And then once you imported that, you can call a column, and then columns acts like array. Sometimes it's a little bit tricky, but largely they act like arrays. So you can call the column by the column header. Say for example, I can, for this table specifically, I can call like maybe data square bracket string A, and then it'll give me this column. So it'll output me like 1 for 5. You can also call the nth row, but rows are indexed by like in a similar way that we talked before many times already, by like a number, right? So the nth column is it can be called by doing this data n, and then from m to n, ladder not included, it's gonna be m colon and then n, right? I'll show you an example later. Right, that's the Wednesday lecture. Let's not do that. So I'm gonna show you guys some example. We have more than enough time, which is great. And I don't even know where the files is, but I don't care. So let's use the, what should we use? Okay, this is gonna be embarrassing, but sorry, let me go to the files first. In the meanwhile, any questions? I'm sad. Desktop research and okay, let me share my screen again. Panda is not superior, come on. Where is my Chrome? Oh. Right, so let me just use my data, my own data, like the data from my research, which means I need to copy the stupid code first. Right. Is this the one? Good. All right. So first we do this import astropy, the units. Let me show you some examples of the units. And then we do this by doing astropy the units as u, and then I can say length 1 equals I don't know, 7 centimeter. Length 2 equals 8 times centimeter, right? Or like maybe light years. No, let's not use light years. Who use light years? Let's use parsecs, right? Or kilometer. Let's use kilometer. This is better. And I want to find the area of a rectangle with like 2 lengths of this, right? So the area of a rectangle is like A equals length times width, right? So area is length 1 multiplied by length 2. That's it. And then you call area. Oh, you call area, then you would get this stupid number over here, which is like 56 centimeter times kilometer, which is indeed the unit for area, but you can convert that to some units that we know, like say kilometer squared, right? So that means area 2, which is the unit conversion, u dot kilometer squared, right? So and these units, they work almost identically as like floats. So you can just do like mathematical operations on those, right? And then it'll give you like the 0.0056 kilometers squared. And I can do like maybe parsec squared, which is some stupid units there. It'll give me that as well, right? So this is how units work. I can also like maybe do, and then let's do a combination of like units and constants, right? So I can also import astropy constants. And then I don't know, let's use gravity, right? I mean, like everyone knows gravity. So I can do G equals constant G. This just literally assigns gravitational constant. If I call G here, you can see like it gives you the value. This value here is rounded, but really it's like the entire float up to today's precision, I guess. And the unit comes with it. So like you can just work with those. So gravity, so force, the force of gravity is G times m squared. Let's just say m squared over r squared, right? But notice I don't have like my mass and radius over here. So let's say mass equals 1 solar mass, right? What is 1 solar mass? I don't know, 2 times 33 gram, 2 times 10 to the 33 grams or something like that. So, but I can just do like 1 times u of solar mass, right? So, so mass, right? And then, really, oh, sure. And then if I do m, it'll give me like 1 solar mass. Like I don't have to convert that to like some like stupid CGS units, right? I mean, like I can just do like 1 solar mass or m sun. That also works. It'll give you like 1 solar mass, right? Radius, I can do solar radius, 1 times r sun, or like so rad. Either way works. And if I call r, it's gonna give me one solar radius, right? So now I can do the force of gravity, right? So force of gravity is G times m squared over r squared, right? Approximately, there's like a 5/3, sorry, 3/5 over there. Let's just multiply that. So, and then if I call Fg, it'll give me this stupid units, right? I mean, but we know force is in units of newtons, or like, what is it? Dimes? No, let's not use that. So like Fg, I can convert that to newtons, right? And then it'll give me like it's 3.2 times 10 to the 32 newtons over here, right? So this is how it works. Similarly, you can like assign, like I said before, like this c equals constant c. That just gives you the speed of light, which is 3 times 10 to the 10 centimeters, which is over here per second, right? So it'll just give you the units directly, and you can work with it. So this is one thing. Another thing is coordinate transformation, which means I need to copy this code to God damn it, sorry, to get my data. So this is the data that I use for my research. Well, one of my research. Import astropedal table as table, like we said before. And then I just copy this code, like I said before, here is table.read. And then it's gonna give me like what's inside is just the path to your file. If the file is in the same directory as your Jupyter notebook, you can just put the name of the file in it. But like since it is not in my case, I put the entire path over here. And then I can just run it. Oh God. What does that even mean? Excuse me? Anyone? Help.
Here, I'll look at it right now. I'll look at the documentation, make sure you didn't make a typo.
No, I don't think I made a typo. I mean, everything is over here, and it was working here.
You could just copy the line from your research.
Like literally, that's what I did.
Oh, that's why. From, yeah. It should be table.table read. Like the way that you imported it, you use it from, there. Because you were importing the whole library as table, but you wanted the table function.
Okay, there it is.
There you go.
God, that was embarrassing. Now it's working.
It happens to everyone.
Right. So, and then I have like scopes and those underscore stars, and then if I call this, you see the table in its full glory. Sounds like Eugene. But then, see, like we have the stars over here, the name of the stars, where this star, what's the mass of these stars, what the spectral type, I don't know, brightness, radial velocity, we have everything. But what we want in this case is RA and DEC, right? Let's show us how table works first. So I can, like, for simplicity, let's just call this data, right? So same thing as before, just change the name. And then so I can say data, I want, I don't know, like the first row or the 0th row, which is here. This is HD147220, this star over here. I can just call like data 0. And then it'll give me the 0th row, right? And you can just check on it, whatever. If I want a first column, or let's not say the first column, if I want the name of all these stars, right? I can do data, name, and then it'll give me like all the names. Like this entire column, it'll give me the entire column. So this name is really, you have to put this in strings. Remember to put it in strings, okay? If I want the mass column, I can do on this, right? If I want, if I want the mass of the 0th star in the table, I can just do mass.0 like this, and it'll give me like this 1.616 over here, right? And they are also like commutable. Like the two indices, they commute. The commutator is 0. Yeah, and then so data 0 mass and data mass 0 are going to give you the same thing. In most cases, there are some very rare cases where they don't commute, and then you have to like use one over the other, right? If they don't commute, they'll give you an error. So yeah, just don't care. Okay, so this is how you import an AstroPy table, yeah, this is how you import an AstroPy table and work with it, and then you can do additions, multiplications as well. So like I said before, they work like the arrays. Okay, so let's do coordinate transformation, right? So I want RA. RA array equals data dot RA, and then DEC array equals data dot DE. DEC array equals data dot DE, right? And then if I call RA and DEC, what? Oh, sorry. If I call array, then it will give me the array of the RAs. And then if I call DEC array, it'll give me this array with all the declinations of the stars. So let's first visualize this, right? Let's visualize this first. To visualize, we plot it. So import matplotlib, right? And then so we can do plt.scatter, RA array, DEC array. And then you see all the stars. These are like the stars as we see them in the sky. Like these are the position of the stars. Like each dot over here is an object, right? Let's just like this size argument. Let's just change it so that we can visualize them better. And then the x direction is RA in degrees, and then the other direction is DEC in degrees as well, right? I put a label just for you to actually visualize this, right? But now, say for example, I asked you to transform this into galactic coordinates, right? How would I do that? I can do sorry, PLT. I first import sky chord, right? and to import this, and then I can say ICRS equals sky chord, and then RA equals my array, deck equals my deck array, right? Okay, now this gives an error, right? Why? If we look at it, it says longitude instance require units equivalent to rad or something like that, which means, but no units was given. This thing I'm not assigning units, right? So like I said before, we have to assign units to these objects. So I can just assign unit equals degree. I want degree, right? In this case, and then I can just transform this. Now, like this is ICRS. I have a sky chord object. If I call it, you will see each star's coordinates is here in a tuple, right? I can do if I want galactic coordinate, I can do gal equal to, or like galactic equals ICRS transform to, like I said before, transform to galactic. So that's the galactic coordinate system. Oh, why is it not working? Okay, great. Sorry, this is a lowercase. And then I can just call galactic. Then we see all the coordinate system has been transformed into galactic coordinates, which is L and B, and then in degrees over here, right? You may be asking, what about the distance term, right? Since both galactic coordinate and ICRS are 2D, so you only need RA and DEC. But say, for example, if I need galactocentric coordinate system, which is another coordinate system in 3D, it's like Cartesian equivalent in astronomy, then you will add a distance term, the distance argument over here as well, like distance equals something, 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 right? Which I don't have the data of at this point. So now we see what this coordinate transformation does, like to our coordinates, right? Like, so this is ICRS, remember, like this plot that we made. So we do galactic. Sorry, scatter. And then we can do galactic L, which is like calling the L component, right, of this object, and also we can call galactic B, right, and then we plot it, and you can see. Okay, let's restrict this from 250 to 250 to 360, 250 to 360, 280. Okay, sure, whatever. So these are exactly the same objects, but now you see it's sort of like we derotated a little bit, and then the stars' positions, they changed a little bit, relatively speaking. So like we see these two stars over here, those are the two stars here, et cetera, right? So like this is like what coordinate transformation does, like rotation, translation, shifts, or whatever. So you will see like the position of the stars are different in each coordinate system, as we expected. But like with this transform to function, it just does a coordinate transformation, all this matrix multiplication, like in a much easier way and a much faster way as well. If you want to see what are those matrices, go to the documentation of astrobattle coordinates. Okay, this shows you what the matrices are, and you can like even write your own code for this. But normally you don't have to. Yeah. But I think, yeah. So that's all we have today. Right on time. Any questions? This is very dense and very astronomy. Like astronomy. Oh, someone already logged off. That's sad. Okay.
Thank you.
You're welcome.
Thank you.